In this video, let us illustrate the difference between the two methods of finding roots for a nonlinear equation. One is bisection method and another is Newton-Raphson method. Now, as we all know that both of these methods are iterative method in a sense that we first of all we approximate a initial value for the root of a given equation. Say f(x) equal to 0 is the equation and we get a first approximation, let us write it as alpha 0, and then we move on repeating a same procedure. That is iteration, that is what is iteration is all about, and we want to find or we want to fix up the value of the root of this equation. Actually, this is the procedure for any numerical analysis problem. So, these two methods goes more or less hand in hand and they are equal in nature, more or less. In bisection method, we fix up a initial interval a0 b0, let us fix it as a0 b0. This is the initial approximation in which interval the root belongs to, and then we gradually fix the midpoint of the intervals. Let the first midpoint be x1, let us say, and then we fix up another interval either a0 x1 or x1 b0 depending on whether f of a0 and f of x1 are of opposite sign or not. Let us illustrate these two methods with a suitable example. Okay. Now, we take a very simple equation, cubic equation, to illustrate whether how these two methods works. Okay. So, let us first fix up a equation, and we are taking a very simple example, x cube minus 5x plus 3 equal to 0. We can easily solve it using Cardan's rule, as we all know, but here we would like to find the real root of this equation. This has at least one real root, we all know, because since the equation is cubic, it has 3 roots and complex roots occur in pair. So, it must have at least one real root. So, we intend to find that real root, and if we term it or denote it as f(x), this equation, then you can easily see that f0 is 3 and f1 is minus 1. So, we can easily apprehend that 0 1 open interval contains the root as far as Rolle's theorem is concerned. Since f0 and f3 are of opposite sign, so the open interval 0 1 contains the root. It is clear. Now, what is the middle point of this interval? It is 0.5, and we check the sign of f 0.5. If we put half here, it becomes 1 by 8 minus 5 by 2 plus 3. So, it becomes 1 by 8 minus 5 by 2 plus 3. 1 by 8 minus 5 by 2 plus 3. And if we roughly calculate it, the denominator is 8 and in the numerator we have 1 minus 4 5s are 20, 4 2s are 8 and 4 5s are 20, and this is plus 3 8s are 24. So it is actually becoming 5 by 8, isn't it? So it is becoming, sorry, it is becoming 19 by 8. What it is becoming? 8 here. So there is 1 minus 20 and plus 24. So 5 by 8. I am right? 5 by 8. Actually, we don't require to find the exact value. What we exactly want to know is that whether f 0.5 is negative or positive, and we can easily infer that it is positive, since 1 by 8 minus 5 by 2 plus 3 is positive. So the root lies between, since f1 is negative, so the root lies between 0.5 and 1, isn't it so? And we again have it. What is the middle point of 0.5 and 1? This is 0, this is 1, this is 0.5, and the middle point of 0.5 and 1 is nothing but 0.75. We all know that. So we intend to check the value of f at 0.75. 0.75 is actually nothing but 3 by 4, and if we put the values here, it is a bit laborious. 27 by 64 minus 15 by 4 plus 3, whatever it may be, it turns out to be negative. This can easily be calculated or inferred, isn't it so? 27 by 64 minus 5 by 4, actually 0.75 is nothing but 3 by 4. So 5 into 3 by 4 is 15 by 4, and here it is plus. So if we calculate it, since 15 by 4 is almost 4 and 27 by 64 is much less than half, so this is negative. So this we can infer, you people can calculate it. So our since f of minus 1 is negative and f 0.75 is also negative, so we choose this interval. What is this interval? 0.5 and 0.75, because at 0.5 f of 0.5 is positive. We have seen it, f of 0.5 is positive. So our interest lies on the interval 0.5 and 0.75, isn't it so? Since here f is negative and here f is positive. Remember that we have calculated f half to be positive. 1 by 8 minus 5 by 2 plus 3, actually, which is turning out to be 5 by 8, and this is positive. So since this is positive and f 0.75 is negative, so our interval is this, and again we have it, we choose the middle point of it. What is the middle point of it? 0.5 plus 0.75 by 2, which is 0.125 by 2, isn't it so? And the middle point of 0.5 and 0.75 turns out to be 0.625. And again we have to calculate determine the sign of f x, or sign of f of 0.625, and the sign of f of 0.625 turns out to be again positive. So what is our, since f of 0.625 is positive while f of 0.75 is negative, we have calculated f of 0.75 as a negative value. What is f of 0.75? 3 by 4. So it is 27 by 64 minus 15 by 3 5s are 15 by 4 plus 3, and if we calculate it, it turns out to be negative, and f of 0.625 is positive. So the root lies in between the root lies in between 0.625 and 0.75. The root lies between this interval. Okay, so again we have to choose the middle point of this interval. So what is the middle point of this interval? This turns out to be 0.625 plus 0.75 by 2, which is actually 0.6875. 6875. And f of 0.6875 turns out to be negative. Since f of 0.6875 turns out to be negative, our interval of concern becomes this. Isn't it so? Because here it is positive and here it is negative. And again we have to halve this interval. And when we halve this interval, we get the middle point of this interval as 0.656. This plus this by 2 gives us the middle point of this interval as 0.656. And if we calculate f of 0.656, if we calculate f of 0.656, it comes out to be almost 0. Almost 0 means this. So, up to 2 decimal places, we can infer that this is the root of this equation. That is the idea of getting the root with the help of bisection method. Now, let us illustrate the method of Newton-Raphson employed in this same equation, and we will see that how it differs. Just remember that in case of Newton-Raphson method, what we do is that we initially fix up a approximated value of the root of this equation to be alpha naught, and then we correct this initial approximation alpha naught with the formula f of alpha naught by f prime alpha naught. Okay. So, this is the formula of Newton-Raphson method. So, the first step to find the root of this equation with the help of Newton-Raphson method is to find the derivative of this function. Fx is this. Let us write fx. Let us write fx as this. So, what is f prime x? It is 3x square minus 5. So, what is the initial approximation? Let us choose the initial approximation as 0.5. We can easily take it as 0.5 because f0 is positive and f1 is negative. So, the root lies between 0 and 1, and we take 0.5 to be the initial approximation. And you can easily calculate f0.5, which is nothing but 5 by 8. 1 by 8 minus 5 by 2 plus 3, which turns out to be 5 by 8 positive. F of 0.5 is turning out to be positive. So, this is our initial approximation. So, what will be the corrected value? Alpha 1. It will be 0.5 minus f of 0.5 by f prime 0.5, isn't it so? So, it is fairly simple. Just put half here. So, this becomes 3 by 4 minus 5, isn't it so? And if we calculate it, it becomes 0.647. It becomes 0.647. One can easily calculate it. It becomes the f of 0.5 is nothing but what I said, 5 by 8, which is actually 0.625. Okay, it is 0.625. It is 0.625. You can check it. And what is f prime 0.5? Just put half here. So, it is 3 by 4 minus 5, which can easily be calculated. Gives minus 4.25. And if you calculate this, it comes out to be 0.647. So, this is the first correction. And then what is alpha 2? Alpha 2 will be the next correction, and it is an iterative process. So, since alpha 1 is 0.647, alpha 1 is 0.647, according to the formula, alpha 2 will be equal to alpha 1 minus f alpha 1 by f prime alpha 1. And since alpha 1 is nothing but 0.647, so we would like to write here 0.647 minus f of 0.647 by f prime of 0.647. And with the help of calculator, if you try to find out the value of f of 0.647 and f prime of 0.647, with a little bit of effort, we can easily find out that the values comes out to be 0.0358 divided by, it is coming out to be a minus, so I put a bracket here, 3.744. Okay, it is rounded up, and if you calculate, it adds up and it gives the value 0.656. And if you can remember, in case of bisection method, we have seen that 0.656 is the root of this equation up to 2 decimal place, because f of 0.656 comes out to be 0.001. So if you try to make it more precise, you will have to do this repeatedly to make it more precise up to 3 decimal places after point. So that is a comparative study of two methods, one bisection method and another Newton-Raphson method, to find the roots of a nonlinear equation.